Welcome to TeamPack's solution to the Pacman Capture the Flag tournament by Marco Barasco, Austin McClernand, and Sam Ross. This video will outline different techniques we developed, implemented, and evaluated throughout this project, which were the A-star heuristic search algorithm, the Monte Carlo tree search algorithm, and a goal inference technique to locate enemies. I will also discuss additional features we implemented and provide some concluding remarks and reflections. A-star search. The team decided on implementing the A-star search algorithm to use for our agents. A-star was chosen due to its optimality when used with admissible heuristics and completeness for safe heuristics. Further, all team members had experience implementing the algorithm, so more time could be spent to extend and optimize our A-star implementation to further improve the agent's capabilities. The application for the A-star algorithm in this project was for pathfinding for our agents. Whenever the agent needed to determine the path or the length of the path to a given goal destination, such as a food, a capsule, or an enemy, the agent called the A-star search algorithm to return a path. Cells are highlighted in this playback when they are popped from the queue during the A-star search algorithm's execution from the red Pacman. We extended this algorithm to also avoid certain cells in the map, such as cells next to an enemy or in a dead end, which will be touched on later. Whilst this sacrificed optimality, it provided a safer path for our agent. Monte Carlo tree search. When the team were discussing potential strategies to improve the action choosing capability of our agents, we recognized that the game state is not just altered by the steps that a single agent takes, but by the actions of all four agents in the game. Thus, we came to the conclusion that it may prove useful to implement an online search algorithm such that the agent does not generate the entire plan at once, but generates it at a single action at a time. This will ensure that our agents were utilizing a far greater proportion of the available information compared with an offline search algorithm such as A-star. The team recognized Monte Carlo tree search as an anytime algorithm, meaning that it could be terminated at any point and provide its current best estimate. Due to the contest having a time constraint on each move, Monte Carlo tree search became a natural choice as we could tailor the number of iterations to maximize the available time and provide its best estimate. Highlighted cells in this playback are for simulations run by the algorithm. This algorithm was not implemented in our final team as its results were inferior to our goal A-star algorithm with a domain-specific decision tree. Goal inference. During the development phase, the team postulated our agents would perform better if they were able to predict the enemy's moves were going to be. This in itself provided a design problem for our agents, as no effort was made to predict where enemies were, if we could not see them, but most importantly, where they were going to be. After much deliberation, one of our team members expressed their previous experience with probability theory and posed a solution to try and track and spy on the enemy's agents. The specific focus for our spy agent is to keep track of the enemy agents. By using the observations passed from the Pacman agents and the noisy values from the game API, the spy agent was able to identify and find the maximum probability cell that a given enemy was going to be in. I will now explain some of the additional features we implemented. Dead end detection. At the commencement of a map, during the 15-second interval to compute, our agents each created a list of all the dead ends in a given map. These were divided into whether they were dead ends in our agent's territory or in the enemy's territory. The results were stored and to be later used by the A-star's path planning algorithm to avoid. As intended, when the agent seeks out a path to search with the A-star algorithm, depending on the game state, the algorithm can avoid these dead ends, thus filtering out potentially dangerous paths and possibilities for our agents to be trapped. They are highlighted in this playback. Two-attacker paradigm. One of the biggest challenges we faced was poorer preliminary results in our earlier agents. During the initial phases of our project, we had designated offensive and defensive agents. Our offensive agent would hunt for food, and the defensive agent would patrol the border of our territory and chase out invaders. After reviewing the matches we lost in our contests, we came to the conclusion that the strongest teams were not concerned with defending their territory, but rather they were effectively racing to get enough food to end the game as quickly as possible. Team Pack adopted this strategy, and our preliminary results went from the bottom 5 to the top 5. Reflections. Overall, our team is incredibly proud of the agents we have developed. Our final submission was 2 offensive agents, following the age-old adage, the best defense is a good offense. If we had more time, the team all agreed we would like to explore implementing Q-learning to direct our agents' behavior, as we believe the domain knowledge required for an effective A-star search reduced the agent's generality.